Okay, we will continue with the third part of protein, which is protein classification. So proteins are classified into three main groups, which are simple protein, conjugated proteins, and derived proteins. Now, what is simple protein? Simple protein is when protein hydrolyzed, the product of protein hydrolysis are only amino acids. And example of simple proteins are albumin, globulin, glutein, prolamins, scleroproteins, histones, and also protamines. Now, what is conjugated proteins? Conjugated proteins are when the amino acid part of a protein combined with a non-protein material such as lipid, nucleic acid, or carbohydrate. And the major example of conjugated proteins include phosphoprotein. So based on the name phosphoproteins, the non-protein material is phosphate. Second is lipoproteins. So the non-protein material is lipid. The third one is nucleoproteins. So the non-protein material will be nucleic acid. The fourth one is glycoproteins, and the non-protein material would be carbohydrate. And the last one is chromoproteins. So the non-protein material is colored prosthetic groups, and that includes example like hemoglobin, which give our blood color red, chlorophyll, okay, which give the green color of plants. Another example is myoglobin, okay, and many other colored group. So the third classification of protein is derived proteins. So what is derived protein? So this type of protein are obtained by chemical or enzymatic method, and this is further divided into either primary or secondary derivatives. So what is primary derivatives of a derived protein? So these are the slightly modified protein which are insoluble in water. So the example of these primary derivatives is rennet coagulated casein. So rennet is an enzyme obtained from the cow, and it is used to coagulate casein, okay, from milk. Okay. So the second type of derivative is secondary derivatives. Okay, so these type of derivatives are extensively changed, which include protease, peptone, and also peptide. The difference between secondary the difference between group like protease, peptone, and peptide in secondary derivatives are in terms of their size and solubility. All of secondary derivatives are soluble in water, unlike primary derivative, which is insoluble. Secondary derivatives are not coagulated by heat. And lastly, proteose can be precipitated using saturated ammonium sulfate solution. Next, we will look at protein hydrolysis. So hydrolysis means you are breaking down or the peptide bond which link one amino acid to another. Now, how we can hydrolyze protein? We can use either acid or base or water and heat. Now, hydrolysis of protein will give us smaller peptides and amino acids. This hydrolysis is also similar to digestion of protein using enzyme. So when we digest protein using enzyme, we are breaking down the peptide bond also. So protein hydrolysis occur in cell to give amino acid or to provide amino acid for further use in the synthesis of other protein and tissues. So this is example of hydrolysis of a dipeptide bond. So dipeptide bond means you have two amino acid joined with a peptide bond. Okay, and you break the peptide bond either using acid or base in the presence of water and also heat. Okay, so you break it. Okay, you break the peptide bond, giving the individual amino acid. So what are the hydrolysis when these alanine, serine, valine peptides are hydrolyzed? So therefore you should get alanine, serine and valine individual amino acid. Next, we move on to denaturation. So what is denaturation? It's a phenomenon that involves transformation of a well-defined folded structure of a protein formed under physiological conditions to an unfolded state under non-physiological conditions. So what does this mean? It means that you have a folded structure initially of a protein, it becomes unfolded. Similar like you fold clothes. Okay, after folding the cloth, and then you unfold it because you want to use the cloth, so it becomes unfolded. Okay, so that's one example. Okay, simple example of folded to unfolded. Okay, so in terms of protein, it means you are changing the structure of the protein, okay, without disturbing the initial backbone of the peptide bond. Okay, so you have studied the primary structure, secondary structure, tertiary structure and quaternary structure. So unfolding means the structure, for example, initially is quaternary. So when it becomes unfolded, it becomes tertiary and secondary. Okay, but the initial backbone does not break apart. Okay, so that's what it means by denaturation. Now, what are the factors that contribute to the denaturation of proteins? The factors are heat, salt, pH, and also mechanical action. So this figure shows the protein denaturation, okay, from the folded state to unfolded state. So notice that the backbone remain the same here. Okay, from folded becomes unfolded. Okay, tertiary to secondary and then primary. So the backbone still remain intact, no cleavage of the backbone. Denaturation will lead to loss of function. Okay, loss of function. And of course, loss of structure due to the unfolding. We will cover in terms of loss of function later on. Okay, so this is example of factor which contribute to protein denaturation. So the protein will denature when undergo heating, okay, whipping, or addition of acid or salt. So from folded state to unfolded. Okay, so that is denaturation. Okay, so we know that the protein becomes unfolded when it undergo denaturation. So what are the loss of function? Okay, for example, here, when you cook egg, okay, initially the egg is in liquid form, and once you apply heat, what happen is the physical property of the egg will change and it become solid. Okay, solid. So that is loss of function. Okay, from liquid, okay, to solid. Okay, due to coagulation. Okay, too long of cooking can lead to rubbery properties. Okay, so this is another example of protein denaturation, or the unfolding structure of protein. Okay, so what makes them become rubbery? Okay, it becomes rubbery when the protein bonds with another protein, and at the same time it is trapping water in between them. Okay, now denaturation can becomes partially reversible. Okay, for example, when it undergo mechanical action. Okay, in this figure here shows when when an egg is whipped. Okay, whip or whisk. So it will form foam. Okay, due to incorporation of air during the whisking. Okay, and when you left it to stand, this foam will collapse back into liquid. Okay, so that is example of partially reversible. Partially reversible means from foam becomes back to liquid. So these are other type of denaturant for protein. Okay, besides high temperature, low temperature can also denature protein. Okay, means when you put the protein under low temperature, it becomes denatured. Okay, for example, milk. When you put milk in fridge, okay, it will separate, forming the watery part and also solid part. Okay, the third denaturation here is heavy metal. So this heavy metal such as lead, cadmium will react with the disulfide bond of the side chain, which form solid. Okay, the next one is oxygen radical, or any ionizing radiation. This will permanently damage protein structure. Last one is cheiotropes, for example urea, guanidine hydrochloride. These these cheiotropes are highly denaturing agent and often used in protein folding studies. Okay, this is guanidine chloride and urea. Okay, common denaturing agents. So these graph shows the percentage of protein the percentage of unfolding protein, okay, versus denaturing. Okay, so initially the protein is in folded state. Okay, so when the concentration of denaturant is increased, okay, the percentage of unfolding protein becomes increased too. Okay, initially quite packed here, okay, due to the folding structure of the protein, for example, quaternary, so it becomes unfolded as the denaturant concentration is increased, so it becomes unfolded. So these are the application of denaturation. For example, boiling of an egg. Okay, so that's one example of denaturation. Wiping the skin with alcohol swab for injection. Now there's a purpose or the reason. Before you get an injection, the skin is swabbed with alcohol because you want to ensure that there's no bacteria present, which will affect the injection process. Okay, so bacteria mostly are made of protein, so when alcohol swab is applied, it will denature the bacteria itself. Okay, so it will ensure there's no bacterial infection when you undergo injection. The third one is cooking. There's reason why you must cook raw food before eaten, okay, to destroy organism like E. coli. Fourth one is autoclave. Okay, autoclave is used to sterilize instrument, means to kill every possible source of contamination. Okay, and lastly, milk heated to make yogurt. So that is one example of denaturation. Okay, to prepare yogurt, milk is heated. Okay, next we move on to the mechanism of protein denaturation. In the native state, the protein is comprises of a hydrophilic surface, okay, and a hydrophobic core. Okay, and during denaturation means it undergoes either non-physiological condition, for example, addition of acid, addition of alkaline, denaturing agent, or under physiological condition like mechanical action, whipping, okay, cooking. The hydrophobic core will resurface or will be introduced to the surface. Okay, this is where the unfolding begins. Okay, so it forces the hydrophobic core to the surface, and when it goes to the surface, it aggregated with the another native molecule of protein, and that is why denatured protein change in terms of physical appearance. So initially liquid egg, after boiling, becomes solid hard boiled egg. So what are the consequences of denaturation? First is improve in terms of digestibility. So denatured proteins are more digestible compared to the native protein. Secondly, when protein undergo denaturation, of course, it will lead to loss of solubility, okay, due to the surfacing of the hydrophobic core. So denatured protein will have a greater tendency to aggregate. Thirdly is change in texture. So protein denatured, of course, would change in terms of the texture. The fourth one is denaturation of protein will improve forming and emulsifying property. So back to the earlier slides, when protein undergo mechanical action, whipping or whisking, it will form foam. So denaturation of protein have better forming characteristic. Emulsifying also will be better, okay, because denatured protein will have both hydrophobic and hydrophilic characteristic. So that is why soy protein is used to increase forming and emulsing for property when they becomes denatured. Okay, so if you look at chocolate packaging, you have you will see one of the ingredient is soy protein lecithin. So lecithin is the emulsifier, okay, used to mix non-polar component and polar component of the chocolate. Last consequences of protein denaturation is affecting the sensory of the product. Okay, for example, in beverages containing protein, the solubility of the beverages, of course, has to be high. Okay, the solubility of the protein in the beverages has to be high. So therefore, if during processing leads to denaturation of the protein, it will lead to precipitation and flocculation during the storage, and therefore it will affect the sensory of the product. It is no longer in a soluble form, okay, it becomes mixture of solid and liquid, which is undesirable. So look at this question here. Tannic acid is used to form a scab on a burn. An egg becomes hard boiled when placed in hot water. So what are the similarity between these two processes here? Okay, both leads to protein denaturation. Okay, the first one is acid as the denaturant, and the second one is heat as the denaturing agent. So next we look at what are the major interaction which influence the solubility characteristic of a protein. So the first one is hydrophobic interaction. So when protein and protein, one native state of a protein interact with another state of protein, okay, this will result in decrease in solubility when it becomes denatured, okay, because the inner core of the hydrophobic surfaces, so it tends to agglomerate. So when it agglomerate, therefore solubility decrease. Secondly is ionic interaction. Ionic interaction normally occur between protein and water, and when water is very powerful polar solvent, so it will result to it results in increased solubility between the protein. Okay. So if the major interaction are hydrophobic, means the protein solubility decrease. Major interaction is caused by ionic, means high solubility. Now protein solubility also dictated by the hydrophilicity and hydrophobicity of the protein surface that is in contact with the surrounding water. Go back to the native structure of protein, in which the inner part, the inner core is hydrophobic and the surface is hydrophilic. So if major hydrophilic is on the surface, means it is soluble. If most of the side chain of the amino acids are the nonpolar or the hydrophobic, it is lower in terms of solubility. So few number of surface hydrophobic, so better solubility. Okay, next we look at protein solubility. So based on solubility, protein are classified into 4 category. 4 category means soluble in water, soluble in neutral condition, soluble in acid or alkaline solution, soluble in ethanol. First we look at albumin. If you notice, all of the listed protein here are the simple type of protein. Okay, albumin normally found in protein whey milk, is soluble in water at pH 6.6. Globulin, for example, can be found as glycine in soybean, and also in milk, soluble at neutral condition. Glutenin and prolamine are highly hydrophobic proteins, and glutenin can be found in rice and also wheat, and soluble only in very acidic and very alkaline condition. Prolamine, soluble in 70% ethanol and can be found in corn and also wheat. Scleroprotein, insoluble in water and also neutral solvent. An example of scleroprotein are the fibrous protein, collagen of muscle tissue, gelatin, elastin, which is a component of tendon, keratin, which is component of hair and hoof. Next is histone. Histone is soluble in water. And then last is protamine, which is strongly basic protein and can be found from herring and scombrin, from mackerel fish. So next we look at factors which affect protein solubility. The first factor is polar solvent. So protein are soluble in strongly polar solvent like water, glycerol, formamide, dimethylformamide, formic acid. Second factor is pH. Now protein are soluble at pH except isoelectric pH, because at isoelectric pH the solubility is minimum. Okay, and this is called isoelectric point. This is where Zwitter ion is formed, which leads to the minimum solubility of protein. So majority of our food protein are acidic protein, okay, which is the sum of aspartic acid and glutamic acid residue. Okay, and these two acid residues are greater if we compare to the sum of lysine, arginine, and histidine residue. So therefore, this majority food classes, food protein containing aspartic acid and glutamic acid residue will have minimum solubility at pH range of 4 to 5, and this is classified as isoelectric pH. And most protein are very soluble at alkaline condition, alkaline pH, which is in the range of pH 8 to 9. So why minimum solubility of protein at isoelectric pH? Go back to the rule of thumb, the hydrophobic interaction and also ionic. So if minimum solubility means the major interaction that contribute to this is hydrophobic interaction. Okay, so lack of electrostatic repulsion, and it will promote aggregation and precipitation. However, there are exceptions. Okay, some food protein are highly soluble at isoelectric pH. For example, beta-lactoglobulin, in which the isoelectric pH is 5.2. And also bovine serum albumin, which is the isoelectric pH is 5.3. Why is this so? Go back again to the rule of thumb. So if it soluble means the major interaction will be hydrophilic interaction or ionic interaction. Okay, so large ratio of surface hydrophilic residue, okay, on the surface of the protein. The next factor is temperature. So as temperature increase, protein solubility also increase, but there's a cut-off temperature, which is 40 degrees Celsius. So more than 40 degrees Celsius, protein solubility will decrease. And why is this so? Denaturation. Remember, denaturation occur at high temperature and water, in the presence of denaturant also. Okay, so therefore protein solubility increase as temperature increase, but only up to 40 degrees Celsius. Okay, next we move on to emulsion. So what is emulsion? So emulsion are fine dispersion of one liquid into another. So basically it involves two immiscible liquid. So generally oil and water, those that does not mix, and one liquid forming the continuous phase, or we call it dispersion medium, and the other will be the dispersed phase or the liquid droplet. And there are four types of emulsion: oil in water, O/W, water in oil, W/O, water in oil in water, or oil in water in oil. Both of these are double emulsion. This figure shows the types of emulsion. The first one is oil in orange color, oil in water, white is water. Second one is water, okay, the white circles are water, blue colored are oil. So water in oil. So the third and the fourth figure here represent double emulsion. Okay, here we have water, white colored, water in oil, orange, in water emulsion. And this one, blue, is oil, white, water in oil. Now, example of oil in water emulsion include milk, cream, mayonnaise, soups, sauces, chocolate milk, and infant formula. Example of water in oil is butter and margarine. Emulsification. So protein are a very good emulsifier. Okay, commonly used emulsifier means they are empiphatic. Okay, having both hydrophilic and hydrophobic characteristics. So therefore, they are able to mix oil and water. So protein emulsion can be used in big products, in ice creams, in salad dressings, and coffee whiteners. An excellent example emulsifier is, as I mentioned previously, is lecithin from soya bean. Okay, soy protein. So to create lecitinated soya proteins, lecithin is mixed with the protein, which make them dispersible. Okay, and then added to the product. Okay. Foaming is defined as colloidal dispersion, where gas phase is dispersed into the liquid phase. In the case of egg white, when you beat the albumin or component of the egg white, the air gets trapped, and this will cause the formation of a foam. That's why the characteristic of foam is light, okay, due to the air that gets trapped, okay, during the whipping or the whisking. Now, foam consists of aqueous, which act as the continuous phase, the egg itself, if that is the material used, and gaseous, which is the air dispersed as the dispersed phase. The texture of foam is similar, like ice cream, like bread, like marshmallow. It has that unique feeling in the mouth due to the air bubbles that dispersed in the aqueous or the continuous phase. Protein stabilized foam can be formed by shaking a protein solution and then it will form a thin layer at the liquid gas interface, and it should be able to incorporate large quantities of gas bubble. So the forming property of a protein is measured based on its ability to form a thin tenacious film at a gas liquid interface, so that large quantity of air bubbles can be incorporated and also stabilized once the foam is formed. So if you notice, when you beat protein, okay, or you beat egg, you will see the foam is at the upper layer, and the lower layer is the remaining liquid that initially was undergo the beating or whisking. Now, formability or forming capacity of a protein can be calculated as overrun. Okay, overrun means steady state form volume, or forming power, or form expansion, and the formula is volume of the foam okay, divided with the volume of the initial liquid used. And then to calculate the forming power, the volume of the gas incorporated divide with the volume of liquid times by 100. So what is the mechanism behind the forming of protein? Okay, let us take egg protein as an example. So when egg protein undergo whisking or beating, it becomes denatured. So means unfolding of the protein structure will happen. So this unfolding will leads to the formation of a long axis of polypeptide chain here. Okay, and this will be parallel to the surface, okay, which is in contact with the air. So one of the property of denaturation is decrease in terms of solubility. So protein will decrease, the egg protein will undergo decrease in solubility, and then at the same time coagulation will occur, okay, between the albumin of the egg component, okay, and this coagulation of this albumin at the same time will entrap at the surface here, okay, entrap air, okay, and it will form at the upper layer, and the lower layer remains the continuous or the aqueous phase. So as you beat harder, okay, or the mechanical action is prolonged, okay, the air is entrapped and it will stretch the albumin, okay. So here is the picture showing forming of egg, okay. So this is the egg, okay. First of all, you broke the egg inside the bowl, and then you whisk it, and as you increase the whipping process, okay, the air will get more entrapped in the stretching of the albumin, and then you get a lightweight of foam material here. And that concludes the third part of protein.